Okay, this is where, in my opinion, this stuff starts getting interesting. We're going to look at composition of the transformations of the plane that we saw a couple of videos back. So before we do this, I want to define just 4 transformations that we can play with. So R20 is going to be the transformation that rotates the plane 20 degrees counterclockwise. R25 will be the one that does it 25 degrees counterclockwise. Fx is going to be the reflection across the x-axis. F slant is going to be the reflection across the line y equals x. So I've got F here for flip and R for rotate. So using flip since reflect and rotate have the same initial. So let's just look at a few of these and figure out what's going on. What would these transformations give us? Some of these are going to be easy, some of them are not. So let's see. First up, R20 after R25. That's a good way to read these is after. Because when you apply these to, if you took this and applied it to some vector x, you do R25 of x first, and then you do R20 of that result. And what you would get would be you rotate the thing 25 degrees and then 20 more degrees. So this would be a rotation of 45 degrees. Counterclockwise. All right, this one's interesting. This one, if you took the inverse of 25 degrees counterclockwise, you turn it clockwise 25 and then counterclockwise 20. And altogether, that's counterclockwise 5 degrees. All right, what about this next one? Flip across the x-axis and then flip across the x-axis again. Well, if you think about what that does, that just undoes itself. You know, you take whatever you've got, and say you've got a triangle here. You flip it across the x-axis, it flips upside down. Then you flip that again, and it goes right back on itself. So this would be no change. Or we'd call that the identity transformation. Because it just undoes itself. The matrix for that, unsurprisingly, is the identity matrix. Okay, what about this one down here? Fy cubed. I don't have that written up here, but this is flipping across the y-axis. If you flip across the y-axis, and then you flip, and this would mean Fy after Fy after Fy. So basically, you flip across the y-axis once, twice, 3 times. So that's the same as just flipping across the y-axis once. And let's see. Before we, well, no, let's go ahead and do this. Flip across the slant and then flip across the x-axis. This one we might need to think about a little bit. Let's say that we had this triangle here. If we start off with this triangle and we flip it across the x-axis, it's going to flip upside down like this to green. Then when we flip it across the slant line, it's going to give us something up here. This is something, I don't know, something kind of like that. It's gonna reflect across there. So what is that? It turns out it's actually a rotation. I'm not really giving you a good explanation of that right now, but just trust me, it's a rotation. Anytime you take two reflections and do one after the other, the result is a rotation. You might say, what about this up here, where we had no change? Well, that's the same as rotating at 0 degrees. Let's look at this one over here now. Notice this is the same as, it's the same two things, but they're as here, but they're done in the opposite order. So again, let's take this little triangle that I drew. I started out with the triangle down here. We're going to flip it across the slant, the line y equals x. When you do that, you get this. And then we're going to flip it across the x-axis to get the final one. Well, if you flip that across the x-axis, it's going to go down here. So the important thing I want you to get out of that is the order matters. So doing this in one order gets us one answer. Doing it in a different order gets us a different answer. So there are a few things to take out of this. These facts. The identity transformation is a rotation of 0 degrees. I already mentioned that. The composition of two rotations is another rotation. That's easy to see. The composition of two reflections is a rotation. That one's not as easy to see, but it's true. And the composition of a reflection and a rotation is a reflection. Now, you can kind of see this just from determinants. Whoops, I was trying to adjust my iPad and I put it to sleep. Let's see. So one thing to recall is this. If you take the determinant of two matrices multiplied together, that's the same as the determinant of one matrix times the determinant of the other. And if you go back and think about it, rotations, the determinant of a rotation is 1, and the determinant of a reflection is -1. And all this stuff up here kind of falls out from that. If you take two rotations and put them together, you'll have two matrices. Both of them will have a determinant of 1, and so the determinant of their product is going to be 1. With two reflections, both of those, if you put two reflections together, each of those has a determinant of -1. So if you do both of them, you get a determinant of the composite matrix of +1. All right, I want to do more of this, but I'm going to put it in the next video.